Hello everyone, we are continuing with the discussion of questions taken from this book, the A-level Topical. This is H2 Chemistry syllabus from 2011 to 2022. The topic that we're going to discuss today is about chemical bonding. Question 1. Which diagram correctly describes the bonding in both Al2Cl6 and AlCl3? The first thing we have to know is whether they form covalent or ionic bonding. Aluminium is a very polarizing ion because it has a large ionic charge and it has small radius. So in other words, it is polarizing due to its high electron density. Whereas Cl- is a rather large anion, so it is quite polarizable. The more polarizing the cation and the more polarizable the anion, the more covalent the bond becomes. We can also take a look at the difference in the electronegativity value of aluminium and chlorine. So aluminium is 1.61 and chlorine is 2.87, and the difference is 1.26. So if the difference in electronegativity is less than 1.8, the covalent character is stronger than the ionic character. So we classify this as a covalent compound. So AlCl3 is covalent, and when it's dissolved in hexane or nonpolar solvents, it will form a dimer Al2Cl6. Now this dimer is formed when the lone pair of chlorine, one of them, binds to the aluminium like this and not the other way around, because aluminium does not have lone pair, so it cannot donate an electron pair to chlorine. So this doesn't happen. This can happen. All right, the answer is D. Question 2. Chlorine is more electronegative than both carbon and selenium. Which molecules are polar? Let's draw out all the molecules first. Carbon has 4 valence electrons, and CSE2 is a linear compound. SeCl2, Se is in group 6, so it has 2 lone pairs of electron and 2 bonds to Cl. And CCl4 is tetrahedral. Which molecules are polar? So selenium is polar because it has a bent shape, whereas CSE2 is linear and that is nonpolar because the dipoles cancel each other, and carbon tetrachloride is also nonpolar. Same thing as CSE2, the dipoles cancel each other. So we can also say that the net dipole moment here is 0. Net dipole moment here is greater than 0. And net dipole moment here is also 0. Answer is D. Question 3. Which bond angle will this theory predict for the HCH bond angle in methanol? If we draw the diagram, methanol has 3 electron domains. 1, 2, 3. So it forms a trigonal planar in which the bonds is 120 degree. Number 4. Water has much higher boiling point than methane. The major reason is because water is a polar compound. All right, methane is non-polar. Now, polar compounds form stronger intermolecular force compared to non-polar compounds of similar size. Now, in water, The difference in electronegativity between oxygen and hydrogen is so great that the intermolecular force is no longer called dipole-dipole, but it's called the hydrogen bond. So strong hydrogen bonds exist. And 2 is wrong because when we boil substances, we do not break the actual covalent bonds, we just overcome the intermolecular force. Yeah, so number 1 only. Answer is C. Question 5. Ethanoic acid forms a double molecule or dimer with molecular formula C2H8O4. This dimer contains 2 hydrogen bonds within a ring of 8 atoms. This is the structure of ethanoic acid. When it forms a dimer, the position of the other ethanoic acid will look like this. So the 2 hydrogen bonds are formed here between this hydrogen and this lone pair on the oxygen, and between this hydrogen to this lone pair. So the 8-membered ring is this part, where we have 2 carbons, 2 hydrogen, and 4 oxygen. Answer is A. Question 6. C2N. Assume that this molecule has carbon-carbon-nitrogen sequence atom, 2 pi bonds, and linear. 2 pi bonds can mean that this molecule has 2 double bonds or 1 triple bond. And it has a total valence electrons of 13. So let's draw them out. In the structure on the left, I have drawn 8 valence electrons. So I'm missing 5. So we can just draw anywhere. 1, 2, 3, 4, 5, like that. It can be other combination. And on the other compound, we can draw 1, 2, 3, 4, 5. There are other possible structures, but in all these cases, there is always 2 lone pairs of electron and 1 unpaired electron. So answer is C. Question 7. Which row about sigma bond and pi bonds in hydrocarbon is correct? Sigma bonds can be formed by either s or p orbitals, for example like this,
And the overlap is head-on overlap.
or it can be formed by 2p orbitals like this, or 2s orbital like this. These are sigma bonds. But pi bonds are only formed by 2p orbitals that have sideway overlap. So the answer is B. Question 8. So let's take a look at the structures. The right structure is the deuterion. So this angle is 107 degree because this nitrogen geometry is trigonal pyramidal with 1 lone pair. This is just tetrahedral 109.5. The next carbon here is trigonal planar 120 degree, and COH bond here, this is a bent shape. This is 104.5 degree because there are 2 lone pairs of electrons. So the missing angle is 107. Answer is B. Number 9. Water, methanol, and methoxymethane have similar shaped molecules. What is the strongest intermolecular force in water, methanol, and methoxymethane? If you have an OH bond, like here, the strongest intermolecular force would be hydrogen bond. Methoxymethane is a polar compound, but it doesn't form hydrogen bond. So the intermolecular force is called permanent dipole. If the molecule is nonpolar, then induced dipole is the intermolecular force. So here the answer is A. Question 10. VSEPR is used to predict the shapes of molecules. Which shape is correctly predicted by VSEPR? Number of bonded electron pair around central atom is 2 and lone pair is 2. That makes a total of 4 electron domains. So the electron geometry is tetrahedral, and these two are lone pairs of electron, so the shape is just bent. So this is correct, it's nonlinear. B is incorrect, it's not tetrahedral. If there are 4 bonded electron pairs, 0 lone pair, then it would be tetrahedral. Now C, number of bonded electron pair around the central atom is 3 and lone pair is 1. So again, we have electron distribution shape of tetrahedral, and one of these is a lone pair. So the molecular geometry is trigonal pyramidal, not planar. Answer is A. Question 11. Which bonding type does not correspond to its description of physical properties? Giant covalent has high melting point. It doesn't conduct electricity when in solution because it's not an ionic compound. So A is incorrect. So the answer should be A. Simple covalent structure, they do have low melting point because simple covalent molecules have weak van der Waals forces, and they do not conduct electricity because they don't have free moving ions. Metallic have high variety of melting points. That is correct, ranging from low melting point like the group 1 metals and also gallium or mercury, and it conducts electricity in solid and molten. Ionic bonding type have high melting point, strong electrostatic force, and conducts electricity when molten because the ions can freely move but not when solid. Question 12. The boiling point of water is 100 degrees and it's greater than that of HF. Which statement is the correct explanation? Both water and hydrogen fluoride are polar and they can both form hydrogen bonds like in the picture below here. But on average, there is more hydrogen bond in water than in hydrogen fluoride. So the answer should be C. There are more hydrogen bonds between water molecules than there are between hydrogen fluoride molecules. Next section, question 1. In which pair of compounds does the first molecule have a net dipole but the second does not? Let's draw the structures. Sulfur has one lone pair of electron and it double bonds with an oxygen and it forms a single bond with one oxygen. So this is actually a dative bond there. And carbon dioxide has a linear structure like this. So the first molecule does have a net dipole because it's not symmetrical. But the second molecule does not have a net dipole. So one is correct. PF3, one lone pair on P, and BF3 is just trigonal planar because boron has 3 valence electrons and it forms 3 covalent bond with fluorine. So there are 3 electron domains. So the first molecule actually has a net dipole moment and the second molecule does not have net dipole moment because the second molecule is completely symmetrical. So 2 is correct. Number 3, bromine pentafluoride. Bromine has 7 valence electrons. So when it forms 5 covalent bonds with fluorine, it will in total have 6 domains. 5 of which are bonding with fluorine and 1 is a lone pair of electron. Whereas silicon tetrafluoride has 4 electron domains and it's symmetrical. So the first molecule has net dipole moment because it's polar, and the second one does not have net dipole moment. So all 1, 2, 3 are correct. The answer is A. So this is the answering key for this section. 1, 2, 3 are correct. It's A. Question 2. From the position of elements present in the periodic table and the physical properties of the compounds, which compounds are covalent? So physical properties could tell us the type of compound, in that covalent compounds usually have low boiling point and ionic compounds have higher boiling point. Right? So these two compounds, they have low boiling point, so probably covalent. And then we can also confirm using the elements. So we have here group 4 elements forming bonds with hydrogen and group 7. So group 4 and group 7 usually bonds covalently, and it's similar with germanium and chlorine. Okay, so those two are covalent. And the third one, aluminium is a group 3 compounds and it's a metal. So usually you would think that metal and non-metal compounds, they form ionic bonds. But since aluminium is a highly charged ion, it's a 3+ ion, so it's very polarizing. That means instead of donating 3 electrons to bromine completely, it polarizes or steals back the electron that it's supposed to donate and forming a partial covalent bond. So there is a lot of covalent characters in aluminum bromide, and therefore our answer would be 1, 2, 3. It's A. Question 3. Which statement correctly describes the graphite lattice? So graphite is carbon atoms forming 3 covalent bonds with 3 other carbons, and there is 1 non-bonded electron, and this electron is then delocalized in the lattice. So the lattice contains delocalized electrons. That's correct. Each carbon atom in the lattice has 3 closest neighbors, and that's correct. It means 3 carbon atoms bonded to it, and the valency of each carbon atom in the lattice is 3. It's actually 4. The valency means the maximum number of single bonds an element can have. So the valency of carbon is still 4, it's not 3. So answer is B. 1 and 2 are correct. Now moving on to the structured question, number 1. Phosgene Cl2C double bond O is a colorless toxic gas. Compare the table below to describe one similarity and one difference between 1s and a 2s orbital, 2s and a 2p orbital. Alright, the first one, 1s and 2s, similarity is this. They are both s orbitals, so they have the same shape, which is a sphere. And the difference is 2s has higher energy and larger radius than 1s. Between 2s and 2p, the similarities are they are from the same principal quantum number, number 2. And the difference is that 2s is a sphere, whereas 2p is a dumbbell shape, and also 2s has lower energy than 2p. State and explain with reference to the valence shell electron pair repulsion theory the shape of phosgene molecule. Okay, so phosgene molecule, the Lewis structure looks like what is on the screen there. The carbon atom has 3 electron domains, and the 3 electron domains are this bond, this and this bond, there is no lone pair of electron on this central carbon. One double bond and two single bonds, and no lone pair of electrons. And therefore, the structural geometry is trigonal planar, and the angle is around 120 degree. All right, of course, the C double bond O, it has higher repulsion than C single bond Cl. So this bond here is actually a little bit more than 120, and this bond here is a little bit less than 120, but we can just say around 120. The molecule of phosgene contains both sigma and pi bonds. Draw label diagram to show how orbitals overlap to form a sigma bond and a pi bond. So our sigma bonds are single bonds and one of the double bond, and our pi bond is on the double bond. Okay, first let's determine the hybridization of carbon central atom, right? Carbon is sp2 hybridized because it forms one double bond. So that means it needs to reserve one p orbital to make a pi bond, right? Whereas our chlorine is sp3 hybridized and oxygen is sp2 hybridized for the same reason as carbon. Oxygen also forms one pi bond, so it needs one p orbital to form that pi bond. So in phosgene, the sigma bond comes from the overlapping of sp2 orbitals, all right? And the way you draw it is something like this. So this is oxygen and carbon. And this type of overlapping is a head-on overlap, okay? And also between sp2 and sp3 of carbon and chlorine, right? So in this image on the right, this is the sp3 of chlorine overlapping with sp2 of carbon, whereas this is the sp2 of carbon overlapping with sp2 of oxygen. Okay, now pi bond is formed when p orbital overlaps with another p orbital, and this is called the sideway overlapping. And when they overlap, the upper lobe and the lower lobe kind of merge and forming this structure over here. These two make one pi bond. This happens between the p orbital of carbon and the p orbital of oxygen. Question 1b. Electronegativity is the relative tendency of an atom in a molecule to attract the shared electrons in a covalent bond. Next, predict all possible intermolecular forces which could exist between phosgene molecules and explain how these forces arise. Alright, phosgene molecules is drawn on the left there, and it's a polar compound. So definitely it has permanent dipole, and it arises because one part of the molecule has a partially positive charged end and also partially negative charged end, and they attract each other. Now, other than PD-PD, phosgene also has instantaneous dipole, induced dipole, and this is caused by the uneven. All right, so all molecules have electrons, and electrons are never still. They always move constantly. So when they move, at one point of time, it happens that one side of the molecule has more electron density than the other side, and this creates what's called as the instantaneous dipole. And instantaneous dipole will induce dipole moment on a neighboring molecule because the instantaneous dipole will distort electron cloud on another molecule, right? And it causes a dipole moment. So that is how instantaneous induced dipoles work. Right? Phosgene reacts with methylamine to form methyl isocyanate, and draw the dot and cross diagram. So I have drawn here the rings. So the Lewis structure should look like this. All right, moving on. In the presence of a catalyst, methyl isocyanate reacts with itself to form compound A. Now look, compound A is formed from 3 methyl isocyanate, right? And it says molecule A does not have dipole moment, so it must be symmetrical and nonpolar. Suggest a possible structure of A. All right, so if you have 3 molecules of methyl isocyanate, they can actually react to form a cyclic structure. And that cyclic structure is actually nonpolar and symmetrical. So this bond is going to break, right? This is going to form bond with another atom, and this is also going to form bond with another atom. So the resulting structure could look something like this. So this comes from one molecule. This is another one molecule. And this is another one molecule. Suggests why at room temperature methyl isocyanate is a gas but A is solid. Now, both compounds have simple molecular structure, but A is a larger molecule. A larger molecule has larger electron cloud, and the larger the electron cloud, the more easily polarized the molecule, and it forms a stronger instantaneous induced dipole, and therefore it requires a higher energy to overcome. Question 2. Olive oil contains a mixture of triesters, which is this one, formed from glycerol and 3 long-chain carboxylic acid. And this table gives the different melting points for different fatty acids. So what we notice here is they all have COOH group at the end because fatty acids are carboxylic acids. And palmitic acid, stearic acid, they don't have C double bond C. So these are saturated, whereas the other 3 are unsaturated because they have C double bond C. And the melting point of saturated fatty acids are higher or much higher than the unsaturated fatty acids. A particular triester found in olive oil melts at negative 15 degree. Explain why this triester melts at a low temperature than any of the individual fatty acids. Whenever you are asked to compare the melting point of different molecules, you always have to think about the intermolecular force, right? So compare the intermolecular force, give the type of the force, and also whether it's stronger or weaker, and how much energy will be required to overcome them. So triesters and fatty acids both have simple molecular structures. Even though the fatty acids are sometimes it's a long chain, but it's not composed of hundreds of atoms, so it's still considered simple molecular structure. And there is a carboxylic acid functional group in fatty acids, so it forms hydrogen bonds, which are the strongest intermolecular force. But triesters do not form hydrogen bonding. They are polar, but they only form permanent dipole, which is weaker than hydrogen bonding. So the more energy is needed to overcome the hydrogen bonding in fatty acids, making the melting point of fatty acids much higher than that of the triesters. Suggests why melting point of stearic acid is higher than that of palmitic acid. So stearic acid and palmitic acid both are saturated, but palmitic acid has a slightly shorter chain than stearic acid. Okay, so stearic acid has a longer chain. That means larger electron cloud, and it's more polarizable, creating a stronger van der Waals in this case. Because we're talking about the carbon chain, it creates a stronger instantaneous induced dipole and requires more energy to overcome. State how the presence of C double bond C bonds affect the melting point of the fatty acid. Well, we saw earlier that the more C double bond C bonds, the lower the melting point. And this is because the molecules become less packed and there is less area of contact between them. And that creates weaker van der Waals, weaker instantaneous induced dipole, and therefore melting point decreases. Question 3. This is about the catalytic converter. The walls of the particle filter are made from silicon carbide, and this is a hard solid that will not melt at high temperature. Suggests how the structure and bonding of silicon carbide makes it resistant to melting even at high temperature. Silicon and carbon, they are both in group 4, so they form giant molecular structures with each other. And because it's a giant molecule, that means they have a lot of strong covalent bonds, and it requires a lot of energy to break. Question 4. Copper does not react with most dilute acid, but some corrosion occurs when oxygen is dissolved in the acid. Suggests why the corrosion is very slow. And this is because there is very high activation energy to overcome the electrostatic force between copper 2 plus and the valence electrons. The higher the ionic charge of the metal cation, the stronger the metallic bonding and the more energy required to overcome the bonding. Describe the structure and bonding in calcium with the aid of a labeled diagram. The structure of calcium will look like this. Calcium is a 2 plus ion, and this is how we describe. Okay, you have to mention the cations surrounded by valence electrons, mention the lattice metallic structure, and that the valence electrons are delocalized, and that there is a strong electrostatic force between the cations and the delocalized electrons. Okay, next, suggest why the melting point of iron is significantly higher than the melting point of calcium. One of the most stable ions of iron is Fe3, whereas calcium only forms one type of ion, calcium 2 plus. So because iron forms a 3 plus ion by releasing 3 valence electrons, this makes the electrostatic force in iron stronger than in calcium. Question 6. Phosphorus 5 oxide dissolves in some polar solvent without reaction, and such solutions conduct electricity. This is due to the presence of the two ions. Draw the structure and suggest the shape of each ion. All right, first we calculate how many valence electrons we are dealing with. So we have a total of 32 electrons in PCl4 plus. That makes 16 pairs. whereas PCl6 minus has 48 valence electrons in total, so that's 24 pairs. So now we arrange all the electrons around phosphorus. Let's first draw 4 chlorine surrounding phosphorus. Now remember, phosphorus is in period 3, so when needed, it can actually form stable atom with more than 8 valence electrons if necessary. But let's just do octet first. So we have drawn 4 pairs of electrons. So we have 12 more to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that is a total of 16 pairs of electrons or 32 electrons. And the whole molecule adopts the positive charge. And because phosphorus has 4 electron domains, it is tetrahedral. Now the other one, phosphorus is bonded to 6 chlorine, right? And each chlorine needs to have 8 valence electrons to satisfy the octet rule. So that's what we're going to do. We have 6 pairs of electron drawn in already. So we need 18 more pairs, all right? We have a total negative charge for this. And since phosphorus has 6 electron domains, this is octahedral structure. That's it for today. Thank you very much for joining me. Bye-bye.